Hey everybody, welcome back. I would assume that you guys have looked at the homework, may not have finished it. Hopefully the time that we take today will not be a ton of time to do a bunch of extra examples. I'm going to give you some time to work in class. Ms. Baribeau will be there to be able to help you as well. I do want to go over just a couple of other kinds of examples that you may end up seeing on the homework. So you'll want to get your curve sketching checklist back out. And you'll also, if you ended up finishing the homework, there's another homework assignment that's due on Monday that involves, I think, 3 other problems from this section, curve sketching. So you'll have 3 other problems that you would be able to work on at the end of class if you've already finished the previous assignment. Okay. So we're going to go back down that checklist one more time with 2 other kinds of examples, and once we finish those, then you'll have some time just to kind of work on your own. All right. So let's start with the example of let's do x over the square root of x squared plus 2. Right? Now you're probably getting sick of the quotient rule now. This one involves some square roots, and I want us to just get a little bit of practice again with some square root stuff. So let's start with domain. In this case, we're worried about roots, and we've got a denominator, so we're kind of worried about both. But one of the things you'll notice is that the bottom is never 0, and it's never negative. So the domain of this function actually ends up being all real numbers again. We don't have any issues that go on with this function. In terms of intercepts, if we look for the y-intercept, that's when x equals 0. And when x is 0, y ends up being 0. So again, we end up with this intercept of 0, 0. And for x-intercepts, we set y equal to 0. So we need the fraction equal to 0. And kind of like we've seen before, fraction only equals 0 if the top is 0. So that means x equals 0, and we're back to... So that is the one point where this function will cross the x-axis and cross the y-axis. It won't cross in any other place. Let's look at symmetry now. So we're going to plug negative x in. When I do that, I get negative x on the top and negative x quantity squared inside that square root. And what ends up happening is you've got that negative from the x, but everything else disappears. So we've got the negative of the original function, which means that we're talking about something that's odd. Okay. That means when I spin my function, it's going to look the same when I spin it 180 degrees. Okay, so now for asymptotes. So for vertical asymptotes, we actually have none, because everything is nice and continuous here. There are no issues with the domain. There are no issues with, we've got no issues under that square root. So we have no vertical asymptotes. When I look at horizontal asymptotes, this is where I look at the limit as x goes to infinity, and then I'll look at the limit as x goes to negative infinity. When I look at going to infinity, this is one of those situations where I find the highest power of x on the bottom. It's x squared, but it's effectively x because it's under a square root. So I'm going to divide by x. Right, x over x is 1. And if I divide by, x squared plus 2. If I divide by x, I really need to turn that into a square root, so I'm going to make it the square root of x squared. I can do that as long as we're positive and that when we're going to infinity, we're positive. So this is the limit as x goes to infinity of 1 over square root of 1 plus 2 over x squared. That ends up being, when x goes to infinity, that term just goes away and I get 1 over root 1. I just get 1. Okay, so when x goes to infinity, this function approaches 1, and it may do that from the top or from the bottom. When x goes to negative infinity, you can probably maybe guess what's going to happen here. Same starting work, we're going to divide by x, but the change here is that in order to turn that x on the bottom into a square root, if I square it and take the square root, I've changed it because I've lost the negative sign. So I have to artificially reintroduce that negative sign back again. Okay, we've done this with a lot of these infinite limits. So what ends up happening here is that I get a negative root on the bottom. And so when I take that limit, I end up getting negative 1. So we actually have y equals 1 and y equals negative 1 as horizontal asymptotes here. Okay, and again, I don't know if this approaches from the top or the bottom. But remember, we have odd symmetry, so what's happening on the right side, we should be able to turn it around, and that's what's happening on the left side. So that also makes sense. What's happening here makes sense from a symmetry standpoint as well. Okay, so now let's look at increasing, decreasing. And we have to differentiate this thing, which I know you're thrilled about. All right, so we've got low, d high, minus high, and when we differentiate the bottom, we got a chain rule, so we have 1/2 the inside to the negative 1/2 times the derivative of the inside. And then we've got the bottom squared, which is just x squared plus 2. Okay, let's clean this up a little bit. The 1/2 and the 2 are going to cancel. All right, I've got a square root there, and here I've got a minus, I've got a fraction because of that negative 1/2. So I've got an x squared on the top, and then the square root of x squared plus 2 on the bottom. Now I don't like having fractions in fractions, so I'm going to multiply through by root x squared plus 2. And what that's going to do is that's going to just give me x squared plus 2 here, minus x squared. And on the bottom, I've got x squared plus 2. I have a whole one here and then another half, so I've got 3 halves of a copy of that. And conveniently, the x squareds cancel. So I've got 2 over x squared plus 2 quantity to the 3 halves. That's not too bad. Notice that there's no place where that does not exist. The bottom is never 0. Everything's fine there. And there's no place where this equals 0 because the top is never 0. So in fact, what's going on here is I have no points to plot here, which means I can pick anything, like 0, and plug it in. I get a positive number here, so the entire thing is positive on that entire interval. So the function is increasing on that entire interval from negative infinity to infinity. There's no local maxes, no local mins. No local maxes, no local mins, no decreasing, right? So that means it's increasing, which means it can't go down and then up and then down. So this is going to have to start down here, go up, and then over like that. Would be, I guess, kind of like it probably looks a lot like another function that you're familiar with, which is arctangent. It actually looks quite a bit like that right now. Now let's look at concavity. I'm guessing it's going to be concave up here and concave down here. In order to check that, actually what I'm going to do, you all know that I hate using the quotient rule, even though that might not seem that way because I keep giving you quotient rule examples. But one of the things that we're going to do here is we're actually going to try to get this in a better form. So the differentiating, I don't have to use the quotient rule. I'm actually going to write this as x squared plus 2 to the negative 3 halves. Now I've just got a constant in that thing. So when I take the second derivative, I can leave the constant alone and then just bring down the power, then make that to subtract another 1 from the power. So negative 3 halves minus 1 is going to give me negative 5 halves. And now the chain rule says I just have to multiply through by the derivative of the inside. So that's much better than trying to do the quotient rule here. Some 2's cancel. Negative 3 times 2, those come together. I get negative 6x. And then this thing to the negative 5 halves actually means it's on the bottom to the 5 halves. That's the second derivative. Notice that there's no place where that does not exist. Again, the bottom is totally fine. But it equals 0 when the top is 0, and that is when x is 0. So testing some things around, if I plugged in a big positive number, the top is negative and the bottom is positive, so I get a negative there. Plugging in a negative number, the top and bottom would both be positive. So as we suspected here, we're concave up on the interval from negative infinity to 0. We're concave down from 0 to infinity, and we end up getting an inflection point right at the origin at 0, 0. And that's what we expected to have happen. We're curved up here and curved down here. We changed concavity right there at the origin. All right? So that is one of the last two things that I wanted to go through, examples that I wanted you to see. Okay. All right, let's do one more and then we will be done here. Okay, let's try the function. Sorry, hold on 1 second. Let me flip and make sure that I'm doing the one that I wanted to here. Let's do 3 times x to the 2/3 minus 2x. Okay. 3 times x to the 2/3 minus 2x. Now, just so you know, because when we're plugging in, sometimes you're not comfortable with that notation. This is the cube root of x squared, in case you need to use that. Okay, so let's start with domain. Now, remember, there's no issues with this. Remember that cube roots, you can actually plug anything in. So the domain here is actually negative infinity to infinity. We have no issues with this function. For intercepts, all right, so again, for the y-intercept, I'm going to let x equal 0. And when x is 0, then plugging 0 into both of these things, I get 0. So 0, 0. I don't do this on purpose, but it just turns out to be, I could throw a +5 on here if I wanted to, and then it wouldn't be 0, 0. But for the x-intercept, I'm going to set y equal to 0. So I'm going to set this thing equal to 0, 3x to the 2/3 minus 2x equal to 0. So one thing that you'll immediately notice is that x equals 0 works. What I can actually do, and hopefully this isn't too confusing, but I can pull 2/3 of an x out, and I'm left with, this is a full x, so I would be left with 1/3 of an x left there. So this part means that x could equal 0. This part right here, if I set that equal to 0, put that to the other side, now I need to, in order to get this to look nice, I need to cube everything. So I'm going to get 27 is 8x. So in other words, x is 27 over 8. That's not all that beautiful, but we cross the x-axis at 0, 0 and 27/8, 0. 27/8 is around 3. It's a little bit bigger than 3. So 1, 2, 3. We're going to cross right there as well. Okay. Now, symmetry, I could try to plug some craziness in, but one thing I want you to notice, just looking at the graph, you can immediately see that we're not going to have any symmetry. There is no symmetry that's going to happen here. Okay? So I'm just going to say none. There's no reason that I even need to check that. Okay, asymptotes. Again, vertical asymptotes, we're not going to have any because we have no issues with the domain. We have no issues with a denominator or something going to 0. For horizontal asymptotes, when x goes to infinity, what's going to happen is that this thing is going to infinity and this thing's going really to negative infinity. But I have a full x here, so this thing is actually much, much, much stronger. It's much bigger. You can kind of think of it, if you want to think of it in this factored form. This thing's going to infinity. This thing's becoming a huge negative number. Positive number times negative number. That overall thing is going to go to negative infinity there. So when x goes to infinity, this overall thing is going to go to negative infinity. When x goes to negative infinity, then what ends up happening is this thing is a positive number, it's something squared. And then this thing right here is actually also going to become a negative times a negative is going to give me a positive. So this thing is also going to, this thing right here is going to positive infinity when x goes to negative infinity. So when x goes to negative infinity, the thing's going up to positive infinity. If that part is confusing, don't get too wrapped up in it. Okay? The point is we don't have horizontal asymptotes. There's no number that this thing is approaching. That's more the important thing that I want you to see here. Okay, now let's look at increasing and decreasing. It's not altogether obvious what's happening here right now. We should be decreasing here, but I don't know if I'm going down and then bumping and up, or bumping here and then going up and down. We'll see what happens here. Okay, so let's differentiate. So the derivative here is 3, and I've got 2/3 x to the negative 1/3 minus 2. Okay, so let's clean that up a little bit. I've got 2 over the cube root of x minus 2. That's my first derivative. Okay, and that does not exist when x is 0 It actually goes vertical. And if I set that equal to 0 to see what happens, I bring the 2 to the other side, and then multiply the cube root over. Divide by 2, the cube root is 1, so x is 1. So that, it turns out that x is being 1. At 0, it does not exist. And then at 1, the derivative is 0. So now if I plug in something huge, I get a small number here, because the bottom is big. I get a small number here, minus 2. I'm going to get negative there. If I plug in a negative number here, the cube root of negative is negative, so I'd have negative minus negative would give me a negative there. And the only time that this is going to be increasing, the function is going to be increasing, the only time when the derivative is positive is in that area right there. So we're going to be decreasing up to 0, increasing to 1, and then decreasing back down to 0. So we're increasing from 0 to 1, and decreasing from negative infinity to 0 and 1 to infinity. And so we have a local max at x equals 1, and we should probably check, because we want to graph that. When x is 1, we have 3 minus 2, so that's at the point 1, comma 1 there. Okay. My computer logged out again. There we go. All right, so we're decreasing down to here, then we're increasing, derivative is 0 here, and then we're decreasing again. Now, one thing that's actually happening, the derivative here, cube root actually ends up with a vertical tangent line here. So we're actually not going to, but we don't have a derivative. It's not going vertical all the way through, it's actually going vertical and bouncing. We need to be increasing. So we end up getting kind of a V shape right there. We're going to be decreasing and then increasing and decreasing. So I don't know what the concavity is going to look like over here, but I'm guessing we're going to be concave down over here. So let's double check that. So for concavity, the first derivative, let me just rewrite it here. It's 2x to the negative 1/3 minus 2. So the second derivative is 2, and then I've got a negative 1/3 x to the negative. I'm going to subtract 1, so negative 1/3 minus 1 is negative 4/3, and the derivative of 2 is just 0. So I've got negative 2 over 3, and then I've got x to the 4/3 there. In other words, negative 2 over, this is the cube root, 3 times the cube root of x to the 4th. So I want you to notice that does not exist at 0, which should not be a surprise. But there's no place where that equals 0. So if I test points around, then notice it's negative, the top is 2, the bottom is 3, bottom's always positive. So overall, that second derivative is always negative, so we're always going to get that this is concave down. So it's concave down from negative infinity to 0, and then from 0 to infinity. There's no inflection points. So the fact that it's concave down means that we're looking at something that's going like that, and it bounces back up and goes back through that point and comes all the way down. So that is the graph of that function. Okay, so you've got some extra time to work on homework, to ask Ms. Baribeau questions, to kind of work together if you'd like to. Be sure that that 3.6 homework gets turned in by latest tomorrow. Tomorrow we're going to be talking about another application. We're going to be setting aside curve sketching. We're going to be talking about another application of derivatives, which is something called optimization. So we'll get to that tomorrow. Have a great day, guys.